welcome to Math 383 complex analysis. And so what I want to do today is I want to finish off the idea of stationary phase. And like a lot of theorems, there are some really nice, strong, severe conditions that just make life great and everything works. And then if you want to become a professional analyst, you can play the game. What is the weakest set of conditions we need to have everything work? We're not going to play that game today. You can look in the book for a weaker set. I'm going to give you a set of conditions today that turn out not to work for the problem that we care about. But they fail by just a small amount. So with a little bit more effort, we can get that to work. Okay. So before we start going into detail, I wanted to just quickly review Taylor series. Everyone should have seen this multiple times. In some sense, we've been doing this because which two words are equivalent in this class? Holomorphic and analytic. And so, here's just some simple code to allow us to plot some Taylor series as well as, manipulating the output. And I'll just, demonstrate a few things here. What function is this almost surely? Yeah, cosine. And so the program is set up so that you can zoom in and you can choose what degree Taylor series you want. And so this is showing just, 0, 2, 4, and 6 term approximations. So we're replacing complicated functions with polynomials. Why am I not showing you the first or the third or the fifth order Taylor series? No. They're the same as the even ones. All the which might be what you mean by 0, is the coefficients of the odd degrees vanish because it's an even function. And so there's really no gain in that. Here's the 24th and the 28th Taylor series approximation. Now, if you only take inputs between minus pi and pi, for all practical purposes, you've nailed the function. And if you're a little bit careless and you go between minus 3 pi and 3 pi, or even further than that, it's still essentially nailing the function. It's remarkable how well this does. And so we can replace complicated functions with simple ones. And this is a key idea in calculus. This is, it seems to have lost it. This is your famous function that causes the trouble, the e to the negative 1 over x squared. And this is just zooming in a little bit on it and just showing what's going on. This is why analysis is so hard. The existence of functions like this, where all of its derivatives at 0 are 0, but the function is not identically 0. If we're looking at the interval from basically negative 0.2 to positive 0.2, we can see, wow, we're talking about a scale of the size 10 to the negative 11. It drops down remarkably fast as you get near the origin. And so one of the big ideas, one of the big things we need to deal with is how well can we approximate something and what are going to be the issues as we do these approximations. So we are going to want to look at integrals of the following form: e to the negative s times phi of x times c of x dx. So phi is going to be real valued. S is going to be a real number. And so let me put that in here. So s greater than 0. Do I have to say s is real if I write this? No, as soon as I write s is greater than 0, that implicitly tells us that s has to be a real number. What do you think should happen to this integral as s gets larger and larger and larger? So it looks like it should be getting smaller and smaller. Why? So it depends on what phi is. So phi is fixed and s is changing. So let's assume we've phi has a minimum at x naught. And so it will depend on whether or not phi is positive or negative at x naught. If phi is positive, then what should happen? It should be getting extremely small because as we increase s, we have even more exponential decay. So we're assuming that phi has a minimum at x naught And we're going to assume that phi prime of x naught equals 0. Okay, I don't necessarily have to have differentiability, but I'm going to assume I have differentiability. I'm going to assume phi double prime of x is greater than 0 in the entire region. So what word would you use, what phrase would you use to describe that plot? Concave up. Excellent, right? So I'm assuming I have a concave up function, minimum at x naught. Now, if I need a little bit more, I'm happy to assume more facts about the third and higher derivatives. If you look at what's going on, because I have an e to the negative s, the greatest contribution is going to come where phi is smallest, right? If I move a little bit away and make phi larger, then because I have an e to the negative s, that's going to magnify that. And so the greatest contribution from the exponential is going to be at the value of x where phi is minimized. Now, I do have this function c next to it, right? And maybe if I move a little bit away, okay, yes, maybe I take a hit with the exponential, but I've got that c, so maybe that makes up for it. Does that seem reasonable? That could be a possible trade. That won't happen because c is independent of s. So even if there's a little bit of a gain in moving, I'm really not going to be able to exploit that as s goes to infinity. So as s goes to infinity, essentially everything that matters is going to be close to x naught. This is a little bit different than what we did last time. When we did the gamma function, we looked at where was the integrand largest, and we saw it was largest at n, and we had n to the n e to the minus n. And we saw that the width, where it was roughly of that size, was a little bit less than order square root of n. So we had a very large region of the integrand where the function was pretty much constant. What we're going to do today is we're going to renormalize things so that rather than having a very large window where the function is approximately constant, we're going to have an extremely small window where the function is approximately constant. So once x moves by just a little bit, because I'm multiplying by s, it's going to really decrease the contribution. So I'm not expecting to move that far. Anybody want to give me a rough guess of how much x can move before things start coming crashing down? If I move s by one whole unit, by half a unit, by 1/1000th of a unit, by 1 over s to the 1/10, by 1 over s to the 1/2, by 1 over s to the 100, how much can I move s by? How much can I move x by? Well, we're multiplying by s. So if we move by just a little bit, so we have p of x is equal to p of x. Phi prime of x naught. It's 0. So we know this term doesn't contribute. Phi of x naught is just a constant. So if I multiply things by s, so I'll put an s here, I'll put an s here, I'll put an s here, I'll put an s here. How much is s phi of x changing? Well, if s times x minus x naught squared is extremely small, I haven't moved that much. So about how big can x minus x naught be before I start to worry? I'm trying to get a feel for the integral before doing any math. Any thoughts about roughly how much can x move from x naught? So if it moves by 1 over s, then that would give me a 1 over s squared from this difference times s, would give me a 1 over s. That's such a small change that I don't think I'd be able to detect it. So I would agree that if I move 1 over s, I'm not going to really see much. maybe 1 over square root, something of that order. Maybe a little bit less, maybe a little bit more, but I would expect something on the order of x moving about 1 over square root of s away from x naught. That's when things should start happening. And this is the advantage of looking at integrals like this before you start doing the calculations. Do I get a feel for what's going on? Once I move more than 1 over square root of s, then I would expect that this contribution is going to be huge and be incredibly damped because of the negative sign. Okay, so I expect that this integral, most of the contribution is going to come from points that are within on the order of 1 over square root of s of x naught. I don't really expect to have to go much further than that to see contributions. Now, let's try to play some calculus games. I don't know if they still teach this, but when I was in school, we plotted underneath the function, we plot the sign of the first derivative and the sign of the second derivative to get a sense of the shape. If the second derivative is positive, what does that tell you? What does that tell you? What information can you glean from the second derivative being positive? The first derivative is increasing. And if the first derivative is increasing, what does that tell you about the function? So just because the first derivative is increasing does not mean the function is increasing.
Oh, yeah.
Right?
Always, but it's increasing.
So my speed could be negative 20 miles per hour. And then my speed could then increase to negative 10 miles per hour. My function is still decreasing. So you've got to be careful, right? So here's my plot. Because I know phi double prime is positive, and I know phi prime of x naught is 0, I know phi prime has to be positive beyond x naught, and it has to be negative before. That's how I know the plot has to look something like this. So I know that, since this is my minimum, I know I'm increasing to the right, I'm decreasing to the left. So when I look at what's going on, I really don't expect there to be much contribution away from x naught. Because if I move just a little bit away, because phi prime is positive, that means my function's increasing. And so once I go a little bit, I've moved up by a small amount, I then magnify it by s, and that small little extra change. Let's say you move up by 1 over a billion. Well, eventually s is going to be a billion factorial to the billion factorial power, something like that. And that will magnify any small gain tremendously. We'll do the calculations a little bit more carefully, but right now I just want to do high level why we expect there to be only a contribution in a small window about x naught. And we think it's roughly on the order of 1 over square root of x, 1 over square root of s for the size of that window.
Would we also see contribution if we move to the left?
No, because over here, things are going to be getting larger than the value at x naught. And so it's also going to be magnified.
Yeah.
So we expect no matter which side you go to, the contribution should be insignificant. Okay, so here is the theorem. Under the above assumptions, and whatever else we need, when we look at this integral, it's equal to e to the negative s phi of x naught times a over the square root of s plus an error of size 1 over s. This just means that the big O of 1 over s means that there's some universal constant such that the error is at most that constant divided by s as s goes to infinity. And a is the square root of 2 pi, c of x naught over phi double prime of x naught to the 1/2. Okay? The square root of 2 pi, by now, what does this make you think of? Gaussian. There really is a Gaussian going on here. So is this reasonable? Let's take a really nice function. Okay, let's assume the following. Let's let phi of x be phi of x naught plus 1/2 phi double prime of x naught, x minus x naught squared. Is that a reasonable choice? That's basically the simplest choice I can take, right? Let's just do this to get a rough feel of what's going on. This is a great way to attack problems. Take something simple, work with the simple case, and then tweak it. All right, so now what would we have? We would have the integral from a to b of e to the negative s phi of x naught, e to the negative s phi double prime x naught, x minus x naught over 2 squared, c of x dx. Yes? Okay, we could already start to see some things working. I can pull out the e to the negative s phi of x naught. What does the x minus x naught squared? Let's just change variables. Let's let t be x minus x naught. And then I'm going to let sigma be 1 over s phi double prime of x naught. And actually, I'm going to have that be sigma squared. Okay. So now when I integrate, t is x minus x naught. So I go from a to b. So this is going to be
b minus x naught.
yeah, a minus x naught to b minus x naught. And then I'll have e to the negative t squared over 2 sigma squared. Because if I have a s phi double prime of x naught in the numerator, that's the same as 1 over that in the denominator. And I'm calling that sigma squared. I've got my c of x. So this is now going to be, I guess, x naught plus t dt. Now, if I have a Gaussian with variance sigma squared, what's the normalization constant? Square root of 2 pi sigma squared, or 1 over square root of 2 pi, and if you want sigma outside. So then that means I have to multiply by 2 pi sigma, and sigma here is 1 over s phi double prime of x naught. And if you look at what's going on now, this looks a lot like a Gaussian. I have this c of x naught plus t, right? But if you look at this Gaussian, when t, so the question is, have I normalized things correctly? Okay. So which value of t is going to be the greatest contribution? When t equals 0. So that's what I'm wondering is, did I normalize things correctly? Yeah. Yeah, it's got to be this way. So t is definitely x minus x naught.
Should you multiply by square root of?
Oh, so sorry. I want the screw root down below. I want the screw root of everything. Sorry, I want the screw root of everything. Yes. So when we look at this, the greatest contribution is going to be when t equals 0. What's the exponential going to be when t equals 0? It's going to be 1. And now, how far can t move before this exponential becomes insignificant? So about how far can t move before this becomes insignificant? What's r?
Wait, am I misreading that? Sigma?
Sigma,
Yeah.
yes.
Right.
So
Thank you.
most when t equals 0, t greater than 1 over sigma makes small. Actually, no, I'm not sure, just sigma. So if t squared over sigma, so if t is less than sigma, then t over sigma is going to be small. I'm going to have something that's like e to the 0, and I would expect it to still be contributing and to still be on the order of 1. Once t is larger than sigma in absolute value, I now have the exponential of a very large negative number, which should essentially be 0. So when I look at this integral, I really don't expect there to be much contribution once t is a little bit larger than sigma. Well, sigma is of size 1 over the square root of s up to a constant, right? So when I'm looking at this, since t really can't be much more than 1 over square root of s, okay, c is a fixed function. I'm moving an extremely small distance from x naught. This is approximately going to be x naught. So this is approximately equal to c of x naught if t is near 0. And that shows you that this is a reasonable result. There is our square root of 2 pi. There's our square root of s phi double prime of 0. This is, yes.
But asking why do we get the most contribution when t is equal to 0?
Well, because you have e to the negative t squared over 2 sigma squared. When is this function largest? This is the exponential.
But like, isn't t taking values from a minus x0 to b minus x0? How do we know that 0 is within this range?
Okay, so we know x naught is between a and b,
Oh, okay.
right? So because of that, we know that 0 has to be in this range. That's what was confusing me as well. Just the way things are normalized. 0 has to be in this range. Yes.
I'm not sure I understand like why the value is like decaying when t is far from sigma, since t is like not s in this case. Like,
Okay. So let's look at it. We get e to the negative t squared over 2 sigma squared. The sigma is 1 over. So if t over sigma, let's say this is of size s to the epsilon. That's big, right? Then that gives you e to the negative s to the epsilon over 2, which is essentially 0. Now let's assume t over sigma is small. Let's say it's of size like 1 over s to the epsilon. Then that's going to give you e to the negative 1 over 2 s to the epsilon. That's essentially e to the negative 0. That's essentially 1. So the idea is if you look at this exponential, its largest value is when t equals 0. So when t equals 0 contributes 1. If you move just a little bit away from t equals 0, as long as you don't move too far, it's still going to be essentially 1. As long as t over sigma is something that's going to 0 with s. So if t over sigma goes to 0 with s, then e to the negative t squared over 2 sigma squared is going to roughly be of size 1. Because you'll have e to essentially 0. If, however, it goes to infinity with s, then this is going to be essentially 0. So this is the high level of what's going on. And so again, before doing all the details, it's, if we can't even do the simple case of phi being the nicest function possible that satisfies these conditions, constant plus constant x minus x naught squared, then we're not going to be able to handle the general case. So when you have problems like this, it's not a bad idea to first just try to get some intuition of what's going on. And then just see, what do we need to make everything rigorous? And so when we're looking at what's going on, a lot of it is just rewriting the expression we have to see the Gaussian. And that's why we're introducing this parameter sigma squared to be 1 over s phi double prime of x naught. That's why we're changing variables t equals x minus x naught. This is now looking a lot like a Gaussian. And the idea is, as we move a little bit away, the contribution is going to be hit by such a small quantity that there's no way it can really matter. Now, what if c is a function whose integral is plus infinity? Well, we could have a little bit of a problem with that. So we need c to have, if the integral of c blows up, it can't blow up too badly. It's got to be such that when we multiply it by an exponential, the resulting integral is going to converge. So you can come up with all the different technical conditions you need. If you assume that a and b is a finite interval, there's no issues. If you assume that c has, maybe c blows up, but maybe it only blows up like 1 over x, so it's not blowing up too badly, then the exponential decay is going to be more than enough to survive, to kill it. Okay. You could probably even have, c is growing no faster than an exponential. And because we're going to have a quadratic term coming in, that should be enough to kill it. Because we know c double prime is greater than 0 for every place other than x naught. So as we move further away from x naught, our function, phi of x, I'm sorry, I think I said c earlier. We know phi double prime at x naught is phi double prime of x naught is what? It's positive. And it's positive on the entire interval. So as we keep moving away, that tells us that the function phi prime is going to be increasing. So then that means your speed is increasing. So then that means the value of the function is going to be going faster than linear. So we should get really good exponential decay. We should be having something decaying faster than linear. So no matter what, if c of x has exponential decay for any fixed constant, we might be able to survive that. But as long as the decay is not too bad, as long as it has some nice decay relative to an exponential function, we're going to be okay. So again, you can try to prove this in as great generality as possible, and then you need to just carefully argue what happens as we move away. And so as we move away from t being 0, we're going to have tremendous decay from the exponential term. But we could have some growth from the c of x naught plus t. But c of x naught plus t, this can't be growing nearly fast enough because this has no s dependence. As we take the limit as s goes to infinity, I'm writing sigma. But instead of writing sigma, I could write something a little bit better. What would be better notation than sigma? Sigma sub s. That's much better notation. Why is it better notation to put in the s? It reminds us that it depends on s. And that what we're really interested in is we're interested in what happens as s goes to infinity. So this is the proof of what happens if we look at the special case where our function phi is given like this. We now have to consider more general phi. Okay? But is everybody comfortable with the analysis here? If not, please speak up, because the algebra gets a little bit worse, which is what you would expect. Right? But morally, what's going on is our conditions tell us, look, in a small neighborhood of x naught, this is what the function big phi looks like. And as soon as you move a reasonable distance away from x naught, we have an e to the negative s times phi of x. That negative s going to infinity, is going to kill the integrand. And so unlike what we had last time, which was over an interval of size on the order of square root of n, Now we have something of size on the order of 1 over square root of s. And again, I might be off by an s to the epsilon or a log of s. I don't care. It's roughly on the size of square root 1 over square root of s. Okay. Any questions on this? All right, so let's try to do things a little bit more carefully now. So we're going to have the integral from a to b of e to the negative s phi of x c of x dx. If you want to, are people happy with, without loss of generality, phi of x naught equals 0? Because otherwise I just pull out that factor in the expansion, right? This is like if I'm integrating over a finite interval, what finite interval am I integrating over? 0, 1, right? Without loss of generality, I'm just going to do that, just make things a little bit nicer. So then I can write phi of x as 1/2 phi double prime of x naught, x minus x naught, plus I'll write order x minus x naught cubed near x naught. And the claim is that near x naught, this is what's going on.
Should that be x minus x naught squared?
Ah, so yes, this should be a squared over here. Thank you. Okay.
By 1.
Taylor series. So the 1/2 is that it's not bad to keep that 1/2. That 1/2 actually plays a role in getting us to the Gaussian because it's 1 over 2 sigma squared. So everything just works out really nicely. All right. So let's change variables. Let's let t equal x minus x naught. So we get basically phi of I'll just keep it like this. Phi of x is going to be 1/2 phi double prime of x naught t squared plus something of order t cubed. And now I'm going to put in my factor of s. Okay. And I want things to stay small. So when I look at the different terms, if I'm looking at this term, what should that tell me about the size of t? Let's write t as s over s to the 1/2. I'm going to put an s to the epsilon. So I could write it in other ways. I'm trying to put in some information that I know. I know that the critical threshold is on the order of 1 over square root. Maybe it's a little bit more, maybe it's a little bit less. So epsilon might be positive, might be negative. I could have done, t equals maybe f of s over square root of s. I could have done it like that. If I don't know what it is, and just give myself a free parameter to play with and see how far can I go. Well, the nicest, the further I go away from x naught, then that means the less integral I have to bound, right? If my main term goes over a larger region about x naught, that leaves less to work with. And it means I'm further away from x naught. What do you expect to happen the further away you are from x naught? What do you expect the contribution to the integral to be the further away you are from x naught? Smaller. So the further away we go from x naught, the easier things are going to be. The problem is then that means we have a large interval near x naught to deal with. So there's a trade-off. If I chose t to be of size, say, s to the 1,000, wow, if t is of size s to the 1,000, I have moved very far away. I expect the integrand to be essentially 0, but now I have such a large interval around x naught that there's a lot of change. So I want to try to balance these competing influences. I want to try to be localized around x naught. All right, so what would the size of this be? So this would be s times s to the 2 epsilon over s. So this would be of size s to the 2 epsilon. Okay, what about the other piece? This would be of size s times s to the 3 epsilon divided by s to the 3 halves. So this would be of size s to the 3 epsilon over s to the 1 half. So when would that be insignificant?
For 3 epsilon less than a half.
Yeah, so if 3 epsilon is less than 1 half, it's going to be small. So epsilon less than 1/6. So if I don't go further than s to the 1/6 over s to the 1 half, then this extra term here is essentially going to be 0 in the exponential. It's not going to really contribute. I don't, yes.
When you say small, is that like compared to linear?
I just mean when I exponentiate it, it's going to be insignificant. So if I look now at e to the s phi of x, that's going to be e to the s, 1 half phi double prime x naught t squared times e to the s order t cubed. But the s order t cubed, approximately how big is that? As s gets really, really large, what does s order t cubed go to in this range? Goes to 0. So what does this piece go to? So this piece goes to 1. So this goes to 1 as s goes to infinity if t is less than s to the 1/6 over s to the 1 half. So what we're saying is that the error in dropping those higher order pieces is insignificant if we go all the way up to s to the 1/6 over square root of s. How many of you have seen basic probability standard deviation? Is it likely to be 2 standard deviations away? No, but there's a positive probability. How about 10 standard deviations away? Very unlikely, but there is a probability, a non-zero probability. If I give you any fixed number of standard deviations, there's a fixed probability. But what if I tell you I want to look at log n standard deviations away as n goes to infinity? Once I give you that the number of standard deviations is going to infinity, then the probability is going to 0. If you've seen Chebyshev's inequality in probability, that's more than enough for something like this. As long as we go a increasing number of standard deviations away, the probability is essentially 0. That's what's going on over here. We saw from the argument before that this is looking a lot like a Gaussian. We've got some issues with how far do we need to go. This is telling us we can basically integrate up to s to the 1/6 standard deviation, something like that. That's tremendous. We're basically saying as many standard deviations as you want, we're going to cover that ground. Okay. That's why the argument we did before now works. We've now reduced to what we had before. And so what we've now shown is that our integral, the integral from a to b of what we had is basically the integral, essentially, x naught minus s to the 1/6 over s to the 1 half, x naught plus s to the 1/6 over s to the 1 half, blah, plus the integral x minus x naught greater than s to the 1/6 over s to the 1 half. Something like this at a very high level. The first piece we do as before, right? And now the second piece, we're now so far away from where we need to be that this should be small. And we're now more than the square root of s away. We have that extra s to the 1/6, so a little bit less than that. You could do 1/10. If you wanted to be cute, you would do 1 over what? Putnam is coming up on Saturday. It's very natural exponent, 1/2023, right? A large number to show that it does not matter, right? I just need something less than 1/600, 1/2023. You should know if 2023 is prime. You should know what the next prime is around that. You should know, are there any nice numbers around 2023? Does anybody know a nice number around 2023? There's a better number than that. 20, not 2024.
25, 24.
Nope.
48.
2048. Why is 2048 nice? Powers of 2. So be aware of that for the Putnam unit. We're close to a nice power of 2 that could come into play. You always want to think about what numbers are going on. So now we just have to show over here that we have exponential decay. Show, good decay as well beyond 1/s. By a factor of s to the epsilon. And that's why that last piece, if you go through and you do the analysis, it shouldn't really matter because we've moved so far away. What I want to do now is I want to apply this to the gamma function. And so much of this is trying to figure out what's the right way to look at things. So here's the gamma integral. The problem with the gamma integral as given to us is that the largest value is when x equals n, or in this case, x equals s. And then the interval in which it was of approximately the same size is on the order of square root of s. Maybe a little bit more, maybe a little bit less, but it's on the order of square root of s. That is the exact opposite of what we just did a moment ago, where we had the integral was concentrated. The other thing is, does this integral match the form we need it to have? Is this of the form that we were looking at a moment ago?
Seems like C has an S.
I'm sorry?
Like we have X to the S.
So that might not be part of, so that can't be part of C. The x to the s can't be part of C. C has to be 1/x, which is not an integrable function, which we might be a little bit worried about, but it's just barely not integrable, so not that worried. Yes. There's always that, but again, we have such rapid decay, I'm not terribly worried. But there's a big concern about matching this up with the theory we just developed. So I'll zoom in a little. What is phi? Yeah, we don't have any s dependence, right? There's no s dependence. I don't have e to the negative s times phi, I just have e to the negative x. So this suggests we need to do a change of variables. Did anybody give me a good change of variables to use? Send x to, I'm sorry? Not x over s.
I mean, s times x.
S times x. Right? Now, if I replace x with s times x, what does dx become? So dx is going to go to s dx. And so I would get gamma of s. The bounds of integration don't change. I'll get e to the negative sx. Now x to the s, that becomes sx to the s, which is s to the s, x to the s, which is s to the s, e to the s log s, right? So I can pull out an s to the s, and I'll have a e to the s log s, and then I'll have a 1/x from the dx over x becomes just dx over x.
S log X.
I think this is right. The x to the s term becomes s to the s e to the, oh, s log x. Yeah, sorry. Log x, sorry. Yes. And so now we have an s to the s, integral from 0 to infinity, e to the negative s x minus the log of x times 1 over x dx. So what would phi of x be? X minus log x. What's phi prime of x? 1 minus 1 over x. Phi prime of what equals 0? 1, right? What's phi double prime of x? 1 over x squared. And that's going to be greater than 0 in our region. So we actually can use our theory for this function. So this is basically the math I grew up with. You know, the table of integrals where you don't have the form in the table of integrals that you have in front of you. You have to do some work to make what you have match what you know how to do. And so we need to have a function phi of x that satisfies all these different conditions. Clearly, this is not going to work as is because of my exponential, there's no s dependence. So I now change variables like this. And now I have a new function. My special point x naught equals 1. My function phi has all the desired properties. And I can basically do everything I want. The only danger, of course, is that as x goes towards 0, 1 over x blows up. And as I go off and integrate to infinity, there's also a problem there. Well, I've got so much decay that I'm really not that worried. As x goes towards 0, what does x minus log x go to? So as x goes to 0, x goes to 0, what does log x go to? Negative infinity. I've got a negative sign in front of that, so it becomes positive infinity. And I've got another negative sign, so I go back to negative infinity. Oh, good. I've got a negative infinity there. I'm not worried about that slight blow up from 1 over x. And similarly, as x goes to positive infinity, I've got an e to the negative s log, an e to the negative sx that's going to be plenty to kill the 1 over x. So in terms of showing that the theory works, you could be generous and say I kind of hand waved over here in terms of handling the error term. In this particular problem, it's going to be very easy to show that the contribution is going to be insignificant as we move away from 1. And so rather than doing things in full rigor, what I thought would be better is to give you a sense of how do you get the correct scale to study the problem? How do we convert an integral we want to do into the formulation that we can use? And then we just go through and we can see that we're going to have the decay that we need. This is similar to doing all these different contour integrals and showing that, well, okay, on this side and this side and this side, they go to 0 in the limit. So it's just going to be the residue theorem.
Yeah, I want to ask, like, whether this new formula for gamma s is going to be an analytic continuation.
So there's a lot of analytic continuation that will go on. And even though this is only defined for real s, this actually extends to complex values of s. Absolutely.
I mean, is the integral below, like,
Yes.
is it?
So as long as the real part of s is going to infinity, we can definitely do arguments like this.
No. I'm asking, is this finite for real part of s greater than 0? Just ask.
Yes. Yeah. Is
it analytic continuation of gamma s, or is it the same thing as gamma s?
You can get analytic continuations from this.
But it's not
in terms of the asymptotics. But
only close for a large s. So
right. In terms of saying that this is a good approximation to gamma of s, if s is small, this is not expected to be a good approximation. You can see the n to the n coming in over here. And we're pulling out the main term. And then the rest is now just going through and doing the calculation. And so now, if you plug in what comes next, we should be getting an s to the s times a. What's a going to be for this problem? And then we'll stop here. So we should be getting an s to the s times a. And a is going to be the square root of 2 pi. And then we have a C of x naught, well, x naught is equal to 1. C is 1 over x, so that's going to give me a 1. And then we have to divide by s to the 1/2. So we would have an s to the 1/2. We have a phi double prime of 0. What's phi double prime of 0 of x naught? That's going to just be a 1. And then we have also an e to the negative s phi of 1. And what is phi of 1 going to be? Just 1. And look, s to the s, e to the negative s square root of 2 pi s to the 1/2. And that's basically gamma of s, which is like s minus 1 factorial. And that's why we have the square root of s down below and not upstairs. All right. So this ends, the electron stationary phase. We're seeing Stirling's formula. And if we wanted, s factorial, we just have to multiply by s. And that would bring the s to the 1/2 upstairs. We got the exponential, we got the s to the s, we got the square root of 2, we got everything. All right. So this is hopefully showing you the power of the method. All right. So we will stop here.